executed correctly, even though you can't see the specific details of the underlying data. It's truly having your cake and eating it too, isn't it?
It really feels like it. Furthermore, Zama offers quite seamless integration into existing developer workflows. Developers can use Solidity, a language they're already familiar with, alongside the FHEVM library. This means they don't have to learn entirely new programming languages or adopt entirely new paradigms to build sophisticated, confidential smart contracts.
That's a big deal for adoption.
Huge. This compatibility allows encrypted dApps built with Zama to interact directly and composably with existing dApps, established tokens, and widely used protocols, fostering much broader adoption and encouraging innovation within the current Web3 ecosystem.
And this essential privacy isn't confined to a single blockchain. Zama provides true cross-chain privacy. The encryption persists across different chains, whether it's Ethereum, Solana, or other networks.
Yeah, no bridging needed, basically.
Yeah, right. That's a crucial distinction. There's no need for users to bridge assets to a new, isolated privacy chain, which often introduces complexity, liquidity fragmentation, and significant security risks. With Zama, your privacy travels seamlessly with your data and assets across the entire multi-chain landscape.
Finally, a hugely important benefit for real-world and institutional adoption is programmable confidentiality. Zama's features allow for selective disclosure. This isn't just about hiding everything. It's about revealing only what's necessary to only who's authorized under specific conditions.
Okay, more granular control.
Exactly. This means you can define precise rules within your smart contract that, for instance, allow a designated regulator or an auditor to decrypt certain specific pieces of data for know your customer or anti-money laundering purposes, while the vast majority of other sensitive information remains completely private to the public. This bridges the critical gap between the need for robust privacy and the unavoidable demands of regulatory oversight, making real-world compliance achievable on a public blockchain.
Now, as with any cutting-edge technology pushing the boundaries of what's possible, there are always limitations and challenges to consider. It's important to acknowledge these trade-offs and understand how Zama plans to overcome them. First, there's the inherent computational overhead. Fully homomorphic encryption, while incredibly powerful, is by its nature computationally intensive. It requires significantly more processing power than traditional plaintext computations.
It's heavy lifting, cryptographically speaking.
Definitely. Zama cleverly mitigates this by offloading these intensive FHE operations to specialized off-chain coprocessors that currently utilize GPU acceleration. On their testnet, this allows them to achieve over 100 transactions per second, TPS, for FHE operations. While 100 plus TPS is an impressive feat for fully encrypted computation, it's still lower than the thousands of TPS that non-encrypted chains like Solana can handle, or even Ethereum's current baseline of, 1530 TPS?
Right, there's still a gap there.
There is. Scaling Zama to thousands of TPS to truly match the throughput of high-volume public blockchains depends heavily on future hardware advancements, like field-programmable gate arrays or FPGAs and application-specific integrated circuit ASICs, which are much more efficient for these specific cryptographic operations. This is a long-term goal that will require significant investment in specialized hardware development.
Another consideration is developer adoption. While Zama provides excellent tools and familiar interfaces like Hardhat and Foundry plugins, writing FHE-compatible smart contracts still introduces new concepts for developers. They need to understand new encrypted data types, like uint for encrypted integers, and grasp the specific limitations of operations you can perform on them within the FHE framework.
Like division being tricky sometimes.
Exactly. For example, not all arithmetic operations are equally efficient, and some, like division, might be particularly challenging or require different approaches. There's a learning curve here, and widespread adoption will naturally take time, despite Zama's strong efforts to simplify the process and provide comprehensive documentation.
It's also crucial for listeners to understand that Zama is still in its relatively early stages of deployment. Their testnet is currently live as of July 2025, allowing developers and early adopters to experiment with building and testing confidential dApps. However, it's important to note, as we discussed, that this testnet is unaudited and explicitly not for production use at this stage. It's a proving ground.
It's still early days for real-world use, yeah.
Right. Looking ahead, the main DApp deployment for Ethereum is planned for Q4 2025, with an ambitious expansion to other EVM chains and Solana slated by the end of that same year. So, while the vision is compelling, the technology is still maturing towards enterprise-ready deployment.
And finally, a point to always consider in decentralized systems. key management risks. While MPC decentralizes key management across those 13 KMS nodes, the system still relies on the integrity of at least 9 of those 13 nodes for decryption. This introduces a very specific trust assumption. While this risk is significantly mitigated by the use of secure hardware enclaves like AWS Nitro enclaves, and by staking incentives for node operators where misbehavior leads to slashing of their staked Zama tokens.
Skin in the game.
Right, skin in the game. But it's still a consideration for any highly sensitive application where absolute trust minimization is paramount. It's a trade-off that balances decentralization with practical performance and security.
So let's circle back to composability, because it's a huge value proposition here. This means you truly don't have to choose between privacy and full participation in the broader Web3 ecosystem. You can genuinely have both. Composability, in this context, refers to the seamless interaction between confidential, Zama-powered, and non-confidential, traditional smart contracts.
They can talk to each other.
Exactly. Developers can write their Solidity-based confidential contracts using the FHEVM library, enabling encrypted operations. These encrypted dApps can then interact directly with existing tokens, establish DeFi protocols, and even NFTs. For example, imagine a scenario where a major institutional investor managing billions in assets previously couldn't touch DeFi because their trading strategies and large order books would be instantly front-run on a public ledger, compromising their entire portfolio.
Big barrier for big money.
Huge. Zama doesn't just hide the trade. It creates a secure, competitive environment where institutions can execute complex, multi-million-dollar DeFi strategies without fear of immediate exploitation. This isn't just about avoiding a few cents in slippage, it's about unlocking trillions in institutional capital for DeFi, fundamentally altering its market structure. You could have a confidential DeFi contract that settles a series of trades privately, ensuring your trading strategy or specific amounts remain hidden while still updating public liquidity pools or interacting with publicly visible token balances.
So the private interacts with the public seamlessly.
Precisely. This allows for incredibly powerful hybrid applications where sensitive operations are encrypted, but they can still seamlessly integrate with the vast and open Web3 infrastructure. It's about building on what's already there, not isolating it.
That seamless integration naturally leads us to cross-chain compatibility, and this raises an important question about how you maintain privacy when data moves between different blockchain ecosystems, which is increasingly common in Web3. Zama's approach to cross-chain compatibility is quite elegant and, again, avoids common pitfalls. Rather than requiring users to bridge assets to a new, dedicated privacy chain, which often introduces significant complexity, liquidity fragmentation, and security vulnerabilities, Zama operates as a confidentiality layer directly on top of existing L1 and L2 blockchains.
And stays where the action is.
Exactly. This means that encryption persists across chains. Your encrypted data on Ethereum can be routed and processed confidentially on Solana or vice versa without decryption. The mechanisms behind this include the Zama Gateway, which acts as a crucial coordinator. It orchestrates these cross-chain operations, validates encrypted inputs, manages access control lists for permissions, and importantly, securely routes encrypted data, what Zama calls ciphertexts, between different chains like Ethereum and Solana.
The traffic controller.
Kind of, yeah. The FHE integration is also key. The FHEVM library is specifically tailored for EVM chains, and Zama is developing similar specialized libraries for non-EVM chains like Solana to ensure broad compatibility. Furthermore, the decentralized coprocessors, which handle those intensive FHE operations, are designed to ensure consistent privacy and computation integrity across these diverse networks. Combined with programmable confidentiality, where decryption permissions are consistently enforced across chains, Zama offers a truly unified privacy layer that integrates seamlessly across different blockchain ecosystems, unlocking new possibilities for interoperable private applications that were previously fragmented.
Here's where it gets really interesting for practical, real-world use cases, especially concerning compliance. Programmable confidentiality. This isn't just about hiding everything. It's about revealing only what's necessary to only who's authorized under specific smart contract-defined conditions.
That selective reveal.
Yes. Programmable confidentiality gives developers precise, granular control over who can access specific encrypted data within their smart contracts. The mechanism works through access control lists, or ACLs, which are intelligently managed by the Zama Gateway. So a smart contract can be explicitly designed to specify, for instance, that only the recipient of an encrypted payment can decrypt the exact amount. Or perhaps a designated regulator or an authorized auditor can decrypt specific pieces of data related to that transaction, such as the source of funds for KYKML purposes. Everyone else on the public blockchain sees only encrypted outputs, maintaining their privacy. Very flexible. Extremely. This allows for highly nuanced privacy settings, far beyond simple all-or-nothing encryption. The benefits are clear and profound. True granular control over data access, which is absolutely essential for regulated industries like traditional finance and healthcare. It enables that crucial selective disclosure for KYC-AML compliance while preserving core user privacy. It basically lets you build dApps that can meet stringent regulatory demands while still providing the robust privacy that users increasingly expect and deserve.
Yeah, it truly balances transparency and confidentiality in a dynamic, programmable way that hasn't been genuinely possible on public blockchains before.
So true.
This profound capability for privacy naturally leads us to a crucial question about practical limits and performance. How does Zama address the scalability challenge, especially given the computational intensity of fully homomorphic encryption?
Right, the speed question.
As we've mentioned, FHE operations require significantly more processing power compared to traditional computations on plaintext data. Zama addresses this through several ingenious mechanisms designed to push those boundaries. Firstly, they efficiently offload those heavy FHE operations to a network of decentralized off-chain coprocessors. These coprocessors do the bulk of the encrypted computation, reducing the burden on the main blockchain. The results of these computations are then verified on-chain using zero-knowledge proofs, which ensures their integrity and correctness without needing to rerun the intensive FHE operation on the main chain.
Verification, not recomputation. Smart.
Very. To incentivize honest behavior and ensure the reliability of these coprocessors, their operators are required to stake Zama tokens. If they act maliciously or try to tamper with results, their staked tokens can be slashed, providing a strong economic deterrent against misbehavior. Secondly, Zama is aggressively pursuing hardware acceleration. They currently employ powerful GPUs within these coprocessors to achieve over 100 transactions per second on their testnet for FHE operations.
Which is a good start.
A significant leap from what's possible with traditional CPUs alone, marking a substantial step towards practical performance. Looking to the near future, Zama has clear plans for even more specialized hardware support, specifically field programmable gate arrays, or FPGAs, and application-specific integrated circuits, ASICs.
The heavy-duty stuff.
Exactly. These are highly optimized chips designed to perform specific cryptographic operations far more efficiently than general-purpose GPUs. They are projected to scale performance to thousands of TPS, making FHE much more viable for high-throughput applications and bringing Zama closer to parity with non-encrypted chains in terms of speed. Lastly, the Zama gateway is meticulously optimized to minimize latency in cross-chain encrypted operations, further supporting scalability in complex multi-chain environments. While the inherent FHE overhead still presents a challenge for raw TPS compared to non-encrypted blockchains like Solana, which can handle thousands, Zama's reliance on these future hardware adoptions is a key part of their long-term scalability strategy to match the demands of mainstream and enterprise adoption.
Okay, let's unpack Zama's architecture because understanding its individual components helps us really see how everything fits together into this cohesive and powerful privacy layer. The FHEVM library is where developers actually get their hands dirty and begin building.
The toolkit.
Right, the toolkit. It's a Solidity-based toolkit specifically designed for EVM-compatible chains like Ethereum and its various Layer 2s. This library fundamentally extends the standard Ethereum virtual machine to natively handle encrypted data types. Think of it like adding new E prefixes to your traditional data types. Instead of an int for an unsigned integer, you'll work with an int for an encrypted unsigned integer and address for an encrypted address.
So, and address, okay.
Exactly. What's truly revolutionary is that it allows developers to perform standard operations like addition, subtraction, or even comparisons directly on this encrypted data, all without ever decrypting it. This incredible capability is powered by Zama's open source TFHE, or Threshold Fully Homomorphic Encryption, scheme. The library is designed to integrate seamlessly with popular Web3 developer tools like Hardhat and Foundry, which streamlines the development and testing process for building confidential smart contracts.
Makes life easier for devs.
For sure. The main challenge for developers, as we touched upon, is a slight learning curve associated with these new encrypted data types, and understanding the specific limitations on certain operations within FHE, for instance. Some FHE schemes might not efficiently support operations like division without additional complexity. However, Zama's tools are designed to make it as accessible as possible, bridging the gap between familiar Solidity development and cutting-edge cryptography.
If we connect this to the bigger picture, host contracts are your on-chain entry points for these private interactions. These are traditional Solidity smart contracts that are deployed directly on the blockchain, just like any other dApp contract.
The front door, basically.
Kind of. Their primary role is to manage encrypted inputs and outputs, and they act as the essential interfaces that trigger those computationally intensive off-chain FHE computations we discussed. They also enforce the crucial access control lists, or ACLs, for programmable confidentiality, defining precisely who has the permission to decrypt certain data under specific conditions. Importantly, these host contracts don't do the heavy FHE computation themselves. That would be far too inefficient for the main chain. Instead, they cleverly send the encrypted data to the off-chain coprocessors for processing, and then they receive the results back, which are then verified on-chain using zero-knowledge proofs.
Checks the work.
Right. This ensures that the integrity of the private computation